Hello guys, I'm back with another video. In this video, we are going to be discussing about how I built a transformer from scratch. I built everything such as encoder, decoder, the layer non-positional encoding, embeddings, tokenizer, everything from scratch based on the attention is all you need paper. What is there in attention is all you need paper is present on the project. So we are going to be taking at the end, we are going to take the Japanese data set with all the Japanese statements, and with the help of our build transformer, we are going to be converting that into English sentence. So let's get into the video, guys. This is the GitHub page of the video. The transformer that we have created, we are going to create is the Konnichiwa transformer. So what it does is that it converts the Japanese and Japanese to English phrase with the help of sequence to sequence translation, and it also has the ASCII punctuation support. This is our Konnichiwa transformers architecture. So the encoder is going to be having 6 layers, and the decoder is also going to have 6 layers. At the encoder, we are going to have the multi-attention head, add a norm, and feed forward, and again add a norm. And in the decoder function, we are going to be having mask, self-attention, and cross-attention, and feed forward network. And before each of the embedding is sent into the encoder or the decoder, we are going to add the positional encoding such as sine and cosine transformation. And for the decoder output, we are going to apply the linear and softmax for getting the probabilities, and then the probabilities will be sent as the output answer for English token translation. And this is the layer of the transformer. We are going to be looking at the layer when we are discussing about the coding, how we have implemented the decoder and the encoder parts. So this is the transformer comparison, guys. So here is the transformer of the attention is all you need, and this is our Konnichiwa transformer. What's the difference is it's just upside down, guys. I just flipped it back and created the Konnichiwa transformer, but both are essentially the same. So that's the architecture of this one, guys. So first, let's get into the tokenizer, guys. This is the entrance of our Konnichiwa transformer. So why I have created this project is basically I've been studying Japanese and I'm expecting the results for my JLPT exam. So at the meantime, I thought of creating something fun. So I started implementing transformer. So entirety of this project is built on PyTorch. So let's get inside, guys. So firstly, we are going to import the repackage, and then we're creating the initiation function. So there are like two things that are essential from the tokenizer, which is the encoding and the decoding port. So that's what we are going to do in the tokenizer. In the special tokens, there are like 4 tokens. Why we need special tokens is we are going to batch the sentence, guys. So each of the batch will have a certain fixed size. If the sentence length is not equal to the size of the batch or the fixed length, it's going to be creating the tensor that we are creating will be having different sizes and formations that will create some extra complexity. So we are going to be having a fixed batch size. So for making the larger sentences small or smaller sentences large, we are going to be adding the special tokens. So for the pad tokens, what it does is it's going to be there on the empty spaces. For example, if I need a 6 batch length and I only have 3 words in it, I will be adding extra 3 pad to it. And SOS is the starting of the sentence, and EOS is the ending of the sentence, and UNK is the unknown words, which are the words that are not present in our vocabulary. It could be something that is not a Japanese word or a certain unknown word. So that's what is going to be present on the unknown tokens. And we are going to create a special token array. So in this array, we are going to have a pad token, SOS, EOS, and the unknown token. So remember guys, here the index is 0, 1, 2, 3, right? So we are having 4 indexes that are already present in the special tokens, and we are going to add it as a list to our vocabulary array. So then we are going to create the two dictionaries, which are word to index and index to word, sequentially for storing the index and the word. So for clean and split functions, for Japanese guys, there's like some ASCII representations, not just exclamations and question marks. Each of the words will be ended with a character like circle called maru. So we are going to be detecting that also. So we are with the help of free, we are going to substitute all these special characters with a special single space. And then for extra spaces, we are going to trim it down to 1 spaces, and then we are going to strip it and split it into a form of list. And then we are going to build the vocabulary. As I said before, there are already 3 sentences present on the special tokens, and then we are going to add all the new words that are coming from our sentences. It's going to be it could be konnichiwa or something. So each of the word will then get appended into the vocabulary, and then we will have a successful vocabulary array built, guys. So that's the clean and split and build vocab function. And then we are going to have the encode function. So this encode function is going to get the sentence, it's going to get the word, and then it's going to convert the word into token IDs, because a transformer or an AI model won't understand something. If you give it like konnichiwa, it won't understand like, oh, it's hello, right? So it's going to convert that entire sentence or words into tokens. So these tokens will be helpful for all the tensor based operations or layer knobs or everything. So we are going to convert the words into tokens here with the help for each words in the sentences. And then for the special tokens, sorry guys. And for the special tokens, we are going to add if there is a special token, we are going to insert that. For example, it could be the start of the sentence special tokens or the end of the sentence special token. We're going to insert it into our already built token IDs. We are going to add the start token and the end token, and then we are going to send the token IDs to the respective function that calls it. And then for decode function, it already does the same, guys. It's relatively the opposite of encode. It's going to convert, it's going to take the words, it's going to take the indexes and it converts into the word. And if there's an unknown word, we are new words as unknown, we are also going to store it in the word. And then we are going to go for special tokens such as EOS or SOS, we are going to skip it, and then we are going to add it to the decode function. We are going to join it, and if there are any extra spaces before the punctuation, we are going to remove it. And then we are going to simply build the vocabulary. This is just a testing function for the simple tokenizer, guys. So this is what the tokenizer does. What it does, it takes the special tokens, converts them into word to index or index to word based on the encoding and decoding. Encoding essentially converts the word to an ID, and decoding essentially converts the ID to the word. That's what the decoder does, guys. And then we're just going to look at the data set over here. For the data set, we are going to be using some masks and stuffs. So yes, guys, this is the second part. The second part is creating a class for the translation data set. So here we have some greetings and common phrases like konnichiwa, hello, ohayo gozaimasu, good morning, and something. So what we're doing is we're going to be creating a small set of pairs. and then we are going to be creating a translation data set. So this data set will be containing all the like source tokenizer, pad IDs, and like it will have a function source tokenizer for tokenizing whatever sentence that is sent by the model or model's encoder or decoder. So it's going to have these functions, and it's going to have the pairs, so the pairs on the list. And then for retrieving the padding IDs, we are going to use the pad token for the source. What's the main motive of translation data set is that we are going to be having source tokenizer and the target tokenizer. So with the help of whenever I call the get item function, it's going to run these things. So what it does is it's going to get the source and token IDs. So this self.encoder tokenizer, let's first get inside that, guys. Where is it? I think yes, we are actually sending it the encode and decode as the source tokenizer and the target tokenizer, guys. So yes, we are going to call the source tokenizer and encode, and we are getting the source IDs and the target IDs, guys. So what it does, it gets the Konnichiwa and it converts that Konnichiwa tokens into source IDs, and it gets hello and converts the hello's tokens into target IDs. So here we are doing this, guys. This is something that is worth to have a note on, because we don't want the model to already know what is the next, because that will create some complexities in training as well. So we want the model to predict the next word. So what we're doing is we are going to be including all the things except the last, and then we are going to include all the things except the first for the label and the input for the model to predict the next, instead of duplication of the input and output. And then we are going to truncate all the source IDs, input IDs, and the labels till the max length. Doing this is we want the batch size of the max sequence length to be fixed. So we are going to convert that into the max sequence length. And for each of the padding, we are going to get the pad length, which is, let's say that we got a sentence of length 20 and we have a max sentence length of 40. We want it to be the fixed size of 40. So we are going to add the extra padding to the sentence. So, and that's what it does over here. And then we are going to add the path values to input and convert to tensor. So tensor is just a matrix representation for our project to have some operations on. So that's what we are going to be doing over here. And then we are going to convert that into a 2D tensor. So in the 2D tensor, we are going to be having the first dimension as the batch. So what's the number of the batch? And heads, you can think of heads like features. For example, if you take the sentence of Konnichiwa, we can think that the heads as the features of it, like grammar, the meaning, or the sentence structure, and what's the sentiment of it. The heads represents the features and stuff. And for tokens, and the third dimension will be the tokens, which is the sequence length. And this is something that is worth noting, guys. What we are going to do is we are going to be creating a mask. Firstly, we are going to create a mask for the source. And for the target also, we are going to be creating a mask, and this mask will contain all the data except the padding, because we don't want any extra computations. For target, there is also a mask called casual mask. We are only concentrating on the target part, guys, not the source, because we want the target to be perfect as possible. And we are having two masks for target. The first one is target pad mask for removing the padding, and the second one is the casual mask. What it does is that it's going to be looking at all the it's going to be looking at everything on the word, but it's going to prevent the future prediction, guys. For example, if you're at the word I, it only knows the word I. If you're at love, it only knows the previous word present in it, not the next word. So as I said before, we want the model to predict the sentences on its own, not just we are inputting all the answers. We want the model to predict on its own. So that's why we are creating an upward triangular matrix. So this matrix will be having all the false values on the right side, because if it on the right side, it will create an upward triangular matrix, indicating that we will predict the future. We will only predict the future only when it's on its current form, not when it's on previous value, right? So that's what the casual mask does, and we are going to be reshape the casual mask to its max length, and we are only going to allow the mask if both the target pad mask and the casual mask are correct. And that's what this one does, guys. We have successfully built the source tokenizer and the target. We have successfully built the translation dataset for the source and the target tokenizer. Okay, guys, so let's move on to the main part, that is the model. Okay, guys, so we are gonna be having some classes over here. Let me just see the class. So yes, guys, so we are having the input embeddings, the positional encoding, and the layer normalization part and scale. Okay, guys, first let's see the input embeddings and the positional encoding. The input embedding combined with the positional encoding will be sent into the transformer, guys. So these both will be combined and sent as an input to the transformer. So let's see what the input embedding does. So I think it is also given on the transformer architecture, guys. We're getting the input embedding and then we got the positional encoding, right? So until now we have seen the translation dataset, the preparation for our work. Now is the actual work, guys. Now is the crisp and the crust of the essentials of the transformer. So let's get into it. So this is the positional encoding, guys. So let's move on. Okay, what we're doing is we're going to get the dimension of the model, and we are going to be having the embedding with the vocabulary size and the dimension of the model. And what we are going to do is we are going to be having a list of embeddings based on the model's dimension. If there are like it could be 4 numbers or as many what the columns essentially mean is the features, guys. So as I said before, the heads, it's going to be representing the feature. That's what it does over here. So it will essentially having a list of embeddings, and then we will be having the okay, these are just things that I included in the comments for like for understanding it better. And yes, guys, we are going to be adding the actual we are going to be adding the matching like effective what is this here is we are going to be adding the square root of the D model. So we are going to add the dimension to the embedding so that the effect of the positional encoding will get reduced, guys. So we got the embeddings, which is representing the possibility of a word over the course of the transformer's training. And then we are going to add the positional encoding to it, guys. So this positional encoding will be having an overall effect on the already present input embedding. To reduce the effect over these, we are going to be adding a square root of the D model. So I think is it given over here? Yes, we want extremely small gradients over here, so we are going to be adding the dot product of a root D dk, which is the dimensional of the model. So that's what we are going to do over here, guys. This is actually 1 by dk, but we are like reciprocaling it, and do it. And then the main thing, that is positional encoding, guys. We are going to include the positional encoding based on two main formulas. The first one is the sine and the second one is the cosine. I think it is given over here, like let me just search it. Where is it? It's beautifully given on the research paper itself. Yes, over here. So we are having the sine and the cosine for the positional encoding. So why we are using both sinusoidal and the cosine function? Because both of it in sine, it will be, I think it's based on the time graph, like 0 to 1, and cosine will be have a negative graph on this. By combining that, we will be having a better representation of the position on the graph. So that's why we are using the sine and the cosine function. So here we are developing the main formulas over here. The divided term, which is the 10,000 power 2i by 3d model. So that's what we are doing over here, guys. We are actually adding the position with, this is the div term over here, and then 0 to 2, which is the sine wave, and the cosine wave is 1 to 2. So this tensor belongs to this and squeeze over here and forward and something, guys. And then we are going to send it as a forward. For sentence 1, we are going to add the embedding plus the positional encoding. And this is what we are going to, we are just adding the positional encoding for each of the sentence over here, and we are adding a dropout rate of, I think, 0.1 to reduce the overfitting, guys. And then we got the layer normalization. What this layer normalization does is it's actually it's a formula for reducing each of the layers based on the mean and normalized mean and variance and normalized forms, guys. So for example, if we have like something dimension, okay, this is for dimension y, we got dimension as -1. So let's see, this is the formula for layer normalization. We are going to be having x minus mean, square root of some beta and stuffs. I think layer normalization formula is also given on the paper. Let's see where it is. It's actually, I think it's not given over here. No, guys, it's not given over here. So let's just see over here. So it's just a general formula for getting the mean and variance recalculation for every token. So yes, guys, that's, we are going to be having okay, so this is for self-attention, guys. That is for the layer normalization. We're just going to apply the layer normalization formula and then it's good to go. Now to the main point. This is the attention mechanism, guys. It's also called scale dot product addition. So this is what we are going to do. Let me get to the main paper. The famous formula, attention Q query key value softmax Q KT root by dk followed by value. So this is the attention. Let's break it down. For each of the query, which is what we are sending, it's going to be creating a key and a value for it. For example, if we get the query, we will look for the transposition of the key and how we will create the QKV, the entire matrix format, is based on this formula, guys, which is we are going to divide the root DK with the mask, soft mask, and then we will get the attention weights. With the weights, we will be adding the value to it, and then we will get the output. Let's see what the code does. So this is getting the last dimension. Here we are transpositioning the K. Over here you can see the K transposition. We are going to do that, and then we are going to be dividing it with the square root of DK. So this is the square root of DK, which is the dimension. And then if there is no mask, which is the padding stuffs, we are not going to do it. And then we are going to apply the softmax to it. So softmax is used for converting into 0 to 1 probability, and then we are going to add some dropouts, and then we are going to multiply the output with the weight. Let's explain what this Q key and value is, guys. Query key and value. The Q is the query. For example, when you say like, hey, what is a cat? Then it will look at all the it will look at the tensor or the key and value pair, key and value matrix that is already present. Oh, I have given here, right? Okay, let's just say that the query input is 32, 10, and 512, which is the dimensionality and the key and values. So what it does is it's going to create the weight for the query, key, and the values. So each of the query, key, and value, oh my god, that is multi-attention. So without the split heads, see it over here. We are going to create the query, key, and value for each of the questions or each of the queries. So let's just say that what is a cat? You'll look at the key, you'll look at the bookshelf, like where is the book for the cat? You will get the key. Okay, this is the book for the cat. You open it, and the value and the information about it is the value. So this is just the general example of how the attention mechanism works. It not just looks at the next word or the next word. It looks at the entire context. It looks at the context of all the words in the matrix. So that's the scale.product attention, guys. We're just going to implement what the formula here is. So we are going to get the query and the key value. We are dividing it, and we get, look at this, guys. Look at the formula. We can actually visualize how the matrix and the search operation is working. We are going to get the query, like what is a cat? Let's just say that we got the weight of a cat, like 0.5, and we get the key of the cat, like 0.2. Now the entirety of the thing divided by the model's dimension, of course, is surrounding on the thing called cat, right? So, and then the value for the cat will be also having a greater probability value. Then we are going to add it, and we will get the exact point of where the cat is. I think you can visualize it, right? So this formula is just amazing. Like you can just find where it is located, and what it essentially does, and where is it located in a precise form with the help of positional encoding like sine and cosine form. Such an amazing formula. Now we are going to have the multi-head attention. So scale product attention, it's only for the attention part. Now we are going to look at the scale product attention. What it does is it's going to, we had the query, key, and value. What we are going to have is we are not going to look at one specific context. For example, if there's a cat, or let's just say a better example, if there's a bank, we are not going to be looking at, hey, bank means a place where you can deposit money. No, we're going to be looking at all the context. As I said before, heads are the features or the context or anything that describes the particular word, right? So each of the head, it will be having a particular context. So it's going to be creating probabilities for all the context. So that is what the essentiality of the multi-head attention. After creating that, we are going to transpose it and join the heads, and then we are going to get the output. For example, let's just say that for token 0 we got like 64 numbers, 64 numbers, 64 numbers, and for each of the token we are going to be creating a representation for each of the heads, for each of the context. For example, bank, the deposit of money, the river bank, or the bank on the other, like, what can I say, a bank, a person's like Steve Banks or something, a bank of the name of the person. So it's going to be creating a matrix like this. For each of the query, it's going to be creating the probabilities of the value of it's going to check the key values of each of the things. This is the multi-head attention layer. So with the help of multi-head attention layer, we will be looking at all the context of a particular key. For example, if we got bank, we will be looking at what the bank is, if it is a money deposition area or a river bank or a name of a person. So it's going to be looking at all the different values. So we are going to be splitting based on the features, and we are going to be computing the attention for all these layers. And then we are going to be doing the multi-head attention layer. So it's going to be generating keys for all this, and we are going to equally divide the head among all dimensions. If there are like 5 total, we are going to divide it based on the number of heads. So it's going to be based on the dimensions and the number of heads, which is the context. So that's the linear transformation, and in the forward functions we are actually doing the essential things, like we are going to be create the dimensions for the query key and value, and then we are going to generate the attention for each of the values, and for each of the heads we are going to generate the attention, and then we are going to join the heads. That's when we will get the WO format. Here is the main formula of the multi-head layer. So yes, we are going to be adding the things over here, attention for each of the query key and value and stuffs. That's the thing. And then to a most essential part known as position-wise feed-forward network. So this network is essential for converting the non-linearity, which is essentially removing the negativities present on a particular matrix, and also enabling the model to learn from a huge dimension by enhancing the dimensions. We can look at over here, guys. So let's just say that the entire dimension of a batch is 512. We are going to apply the linear function. So that's going to result in an enlarged amount of dimension. This will help the particular model to have a large learning space so that it can learn a lot of things on that dimension. Then we are going to apply the ReLU, which is non-linearity, remove the negative functions, and then we are going to use the dropout, essentially reducing the overfitting, and then again produce the dimensions with a linear thing. That's what the position-wise feed-forward does. Now, getting into the most essential part of attention is all you need, which is the encoder layer, guys. So I think as we know everything before, like layers, multi-head attention, the encoder layer is essentially very simple to understand. So it will have a self-attention and layer norm and feed-forward network and layer norm again. Each of the time it will be computed again and again for 6 times for the 6 layers, right? Based on the number of layers. So it's going to be having firstly we are going to have, okay, let's see it over here. Okay, so where's the main thing? Main diagram, I think it's over here. So yes, this is the encoder layer. Okay, so it's going to have the norm, feed forward, multi-head, norm, feed forward, and normalization. So that's what we are doing. We are getting the multi-head attention and stuff. Firstly, we are going to have the attention output. We are normalizing it. we are adding an X over here with a self dropout rate, because we don't want the model to like adding or giving like more information, or like around information, or the information that is not present, resulting in the vanishing gradient problem. We are going to be adding the residual X to maintain the original information. And then we are going to add the feed-forward network, which is enhancing the model to have more learning space. And we are going to do that for the number of layer times. So that is n layers. Here we have used like 6 layers, I think. So we are initializing the encoder layer for each of the number of layers, and then we are going to appending to the encoder, guys. Then we got the second most equally important layer, decode layer, guys. So this decode layer will be having a special attention known as cross attention. We will be looking at, I think, cross attention. Yes, this cross attention will get the original input through the encoder to maintain, to understand the context more. So that's the cross attention, guys. Just look at the encoder input. So we got the self attention output, and then the cross attention output, and then we are essentially doing the same thing and again and again. So mask multi-head attention, so multi-head attention, which is the cross attention, guys. Yes, okay, so that's the decoder, and then we will have the fully assembled transformer. We'll get the input embeddings, positional embeddings, and then we are going to create the encoder and decoder format. Then we are going to encode and decode it with the help of the tokenizer and stuffs, and then we are going to forward it for the output projection, guys. So encoder, so the encoder is where we are encoding the things, and yes, guys, that's the thing. So we're just assembling the transformer. So input embeddings, position, encoder and decoder, just the assemblation of transformer. Now to the main form, that is main function, train.py. So what the train.py does is, it's basically very simple. Now we have understood the very like, there was a saying that like, eat the frog first, like we have eaten the frog. Now it's just the really simple part. So we are just initializing the data set, the tokenizer, and we are creating the transformer with the layers, heads and tops. And then what we are doing is, there's one main important thing that we have to note, is that we are using a loss function called the atom optimizer, loss function and atom optimizer. The loss function will calculate the loss and calculate the gradients, and the optimization will change the model parameters such as learning rate to have a better model. It is also, the atom optimizer is also used in the main paper, I think. I think it's somewhere by self-attention training. Yes, over here. This is the learning rate, guys. So what it does, it's going to get the minimum step number and the step number and warm-up steps. It's basically how many times that particular epochs are running, or just the number of times you are sending it again and again for training. So it's going to get the learning rate. So this optimizer will help us understand the learning rate and modify the parameters accordingly, guys. So that's the thing. And then we are having the epochs. For each of the epoch, it's going to be having the things like target input, target output, and epoch, it's basically the same. Firstly, whenever you're adding a new batch, we are setting the optimizer to 0 grad for removing all for the new loss gradient, and then we are redoing the values, guys, so that the new optimizer will understand what we are doing over here, like how we are adding the things. That's the epoch. And then we are going to add the inference function, like the main function. This is what the transformer does when we run it. So it's going to get the source IDs and it's going to apply the padding marks. It's essentially what we're doing the things before. And then here's the main important word, which is known as the logits. So logits are basically probabilities, guys. And then we are going to train it for each of the transformer sentences. Yes, guys, we have now understood all the source code. I think if we look at the transformer layers, it's going to be a piece of cake for you guys. So that's the essential thing about transformers. Now we are going to look at the source code. Yes, guys, this is the source code. Firstly, we are going to activate the source VNV. I guess it's .vnv, and then we're going to activate it. Yes, guys, so we are going to run the main thing, that is train.py, as I said before. So Python 3 train.py. Let's see, it built the vocabulary we have given already, and I think it's asking for, no, it didn't ask. Let's just wait for it, guys. Yes, it came. So I'm going to get over to the where is that model thing? Yes, dataset. Okay, let's say konnichiwa. It says hello. Let's say, こちらこそはじめまして. Nice to meet you too. Let's say, what can we say next, guys? Okay. This is getting like I need to choose one thing. Let's say, okay, guys. ちょっと待ってください. Let's say this. Wait a moment. ちょっと待ってください. English, wait a moment. Yes, guys, that's the entirety of the transformer, Konnichiwa transformer. If you like the video, please like, subscribe, and share. See you again in the next video. Bye.